Hello everyone. In today's class we will start attention. So sequence to sequence problem was very popular in 2014. In fact, it turned out to be one of the popular models which basically outperformed all the statistical machine translation models that were out there, right? 40 years of statistical machine learning history, statistical machine translation history, right? Suddenly the sequence to sequence model outperformed all the statistical models. Okay, and then in 2016, right, people noticed that some more tweaks or some more modifications can also be done on top of sequence to sequence. Okay, in 2016 a new method was proposed which is called the attention. Okay, now let's look at attention here. So now so far sequence to sequence is also RNN. There are two RNNs, right? There are three problems which still persist. What are the three problems? The first problem is you can't access all the tokens in parallel, right? The first problem. The second problem, if you think about it very carefully, the sequence to sequence model essentially considers each pair of interactions, right? Let's say hidden state t, hidden state t plus 1, this interaction, hidden state 1, hidden state 2, hidden state t plus 5, hidden state t plus 6, every consecutive pair of interactions are considered in a similar way. So the interaction distance is considered as linear, right? So the way we treat 1 versus 2, the way we treat t I minus 1 t, we will treat the same way let's say t plus 5, t plus 6. The third problem is very important. The third problem is called the bottleneck problem. Look at this one. Okay, so this guy, this is the final hidden state of the decoder, right? So this input is fed to the this is the final hidden state of the encoder. This input will be fed to the decoder, right? The decoder has access to only this hidden state, right? For the decoder, this is the input. Decoder doesn't have access to these hidden states, right? So this guy has a lot of responsibility of remembering the entire input sequence, right? So there is a bottleneck on this in terms of remembering the entire sequence of the input, right? If you are not able to compute it properly, you will not be able to process it. But think about it very carefully. The word he corresponds to the word il. The word pi corresponds to the word this, right? But at this time, at this stage, this hidden state has no access to the first hidden state of the decoder of the encoder. So due to vanishing gradient problem, due to other problems, right, over smoothing and etc., it will happen that this hidden state will essentially forget about the first hidden state, right? And when you come here, this guy will completely forget about this one. So instead of this, if we had a direct connection from decoder to encoder, right, that could have solved this problem. Maybe let's say there's a direct connection from he to il, from a direct connection from pi to this one, right? Then that could have solved the problem, because through these shortcuts, right, information can move from encoder to decoder. So this is the philosophy of attention. I already mentioned about this bottleneck problem, right? So what is attention? The core idea here is that on each step of the decoder, we use a direct connection to the encoder to focus on a particular part of the source sequence. So let's look at the architecture first and then we will understand. Let's take a desi example. Okay, हम बाजार गए थे. Okay, and you want to convert this Hindi to English. So in attention, what we do, Now this is my encoder state, right, and this is the final hidden state of the encoder. The first hidden state of the decoder, this will have access to all the previous encoder states, right? And how do we do that? Here we introduce a concept of query and value. Each of these decoder hidden states will act as a query, and each of the encoder hidden states will act as a value, right? So the decoder hidden state will basically check which of the encoder hidden states will be relevant for that decoder state, right? Relevant means which encoder states will be helpful for the decoder state to generate the correct output. Okay, how do you do that? So let's first look at the computation. So this is my query and this is value v. So what I do, I'll first measure the similarity between query and value. And how do we measure this? We measure this using simple dot product. So this vector and this vector will be passed through dot product, right? And we get a scalar here. Scalar, this vector and this vector will pass through dot product, right? And then similarly, this is my query, this is v. So each of the decoder state will basically be used to do the dot product of every encoder state separately. So this is the second dot product, third dot product, fourth dot product. What are these dot products indicating? They are indicating the similarity, right? So these are called attention scores. All of these elements are scalars, remember this. From attention score, I pass them through softmax. Softmax will produce a distribution, and this distribution is called attention distribution. Let's say this is P1, this is P2, this is P3, and this is P4, right? And let's say this is V1, V2, V3, V4. V1, V2, V3, V4 are vectors. P1, P2, they are scalars, right? And from there, from this computation, what I do, I will generate something called attention vector. Attention vector, right? What is the attention vector? Attention vector is the weighted sum of the encoder states. Weighted sum of the encoder states. And what are the weights? Weights are the probabilities. So attention vector will be P1 and the corresponding vector V1 plus P2 V2 plus P3 V3 plus P4 P4. This times this plus this times this, right? And plus so on and so forth, right? So P's are the weights. So what is this vector? This vector is the weighted sum of the encoder state. And how these weights are computed? The weights are computed based on the similarity between the decoder state and the encoder states, right? Remember, these weights will be different when I move to the next decoder state, right? So I got this attention vector. I already have a hidden state here, right? And the attention vector here, which I compute. And then, so this is attention vector and this is the decoder vector, decoder hidden state. I just concatenate them. So at this time, at timestamp 1, hidden state is H1, right? Attention vector is, let's say, A1. I concatenate them, right? And then what I do? I pass it through a linear layer U followed by nonlinearity, and it will generate a probability. So instead of passing the hidden state directly to the linear layer, I will pass this concatenation of hidden state and attention vector, right? So similarly, for the next decoder state, this is my Q and this is my attention distribution. Now look at this distribution of the previous distribution. They are different, right? Now if you look at the distribution carefully, to generate the first output token of the decoder, look at the probability. Which encoder was useful? Which encoder state was useful? The first one was useful. Therefore, the corresponding probability was high. To generate the second input had, which one is useful? The last one was useful. To generate the third one was useful. To generate the fourth one, the second one was useful. Right? And how do we get this usefulness? From the probability, the dot product probability. This is clear? There is no bottleneck problem here. Why there is no bottleneck problem? Now we have a shortcut from every decoder state to all the encoder states. Every decoder state can access all the encoder states. Clear? So this is attention. Now tell me, due to this attention, due to incorporating the attention concept, did I incorporate any additional parameter? Answer me, quick. No, there is no parameter involved. What are the parameters here? The parameters are same: WH, WE, WH dash, WE dash, and here U. That's all. There is no U here. There is no U here. Attention score, attention distribution. There is no U here. So this is vanilla attention. Okay. Of course, there are modified versions of attention I will discuss, but this is the vanilla attention. Okay. So let's look at the equation once again. The attention equation I have already mentioned. So H1, H2, H3. Look at this equation, right? H1, H2, H3, Hn. These are the hidden states. Hidden states of the encoder. E, right? What is ST? ST is the hidden state of the decoder at the TH time period. So ST will basically access all the hidden states of the encoder. So ST H1, ST dot product H1, right? ST dot product H2, and so on and so forth, right? So we generate these numbers. These are dot products. These are attention scores, right? Let's say this is ET. Attention scores will be passed through softmax. So alpha T is the attention distribution, which will act as weights, right? So alpha T will then be act as a weight for each of these hidden states of the decoder. So alpha I, HI, right? T ranges from 1 to n. What is AT? AT is the attention vector, right? Then AT and ST. ST is the hidden state of the decoder. This will be concatenated, right? And then this will be passed through the linear layer. Attention is great. Why? Attention not only gives you a shortcut from decoder to encoder, it also gives you many additional information, right? What are the additional information? It reduces the problem of bottleneck problems, right? I already mentioned. Okay, bottleneck problem will not be there. It will also help address the vanishing gradient problem. Why? Because now there is a shortcut, right? One gradient is moved through this, one gradient is moved through the shortcut. Very similar to skip connection, right? The most important beauty of this attention is that it gives you interpretability. For example, here, based on this distribution, you can say that to generate the last word of the decoder, second word was more responsible. You will not get this kind of information from a vanilla RNN, right? So if somebody tells you, can you explain that why you generated this? You can say that look at the probability. So this is my attention map. So my French inputs and the English outputs, and you see, so this entry, so each of these rows indicates, okay, attention distribution. If one entry is dark, it means the probability is high, right? So to generate the word he, the word ill was responsible. To generate the word with a and pi, the last word of the encoder was responsible. Therefore, Stark, right? So from the attention matrix, you can identify the portions which are responsible. So this will give you an alignment also. So in a statistical machine translation model, which I did not discuss, there are three components. Two components. One is the translation. So you basically, so मैं बाजार जा रहा हूँ, I am going to the market, right? So it is not one-to-one translation. If you think of it carefully, it is not word-by-word translation. Sometimes we need to change things here and there. So in statistical machine translation, there are two components. One is this one-to-one translation, and then you do some alignment. So alignment will rearrange the token, right? So for the alignment, you need a separate model. But here, you do this alignment for free due to this attention. And by the way, sometimes there are papers which claim that attentions are used for interpretability. There are papers which claim that attention can't be used as for interpretability. This is debatable, but therefore I said it gives some interpretability. So I discussed attention with respect to sequence problem, right? But attention is not restricted to sequence problem. Attention can also be used in other models. You can use attention in normal RNN, for example, right? So in general, you can think of this attention as a generic concept in deep learning, where you have a query and you have some values, and you want to measure the importance of query with respect to all the values, right? You can use attention. You can also think of an attention, the attention vector that you generated. Remember, attention vector is one vector that you generated, right? For every decoder hidden state, you generated one attention vector, right? So attention vector can also be thought of as the summary of all the value vectors. Think about it. Attention vector can also be considered as a summary of all the value vectors. In our case, the value vectors are encoder out hidden states. It's a summary, right? Irrespective of the size of the encoder layers. How many encoder layers? Let's say there's a sequence where there are 100 encoder layers. There is another sequence where there are 10 encoder layers. Irrespective of the size of the encoder layers, you can always generate one vector, attention vector, right? So it basically, you can think of attention as a summary of the value vectors. You can think of attention as something which can squash the entire encoder states into a single vector. Okay, why I said all these things? Because when you apply attention to some other problems, you need to understand all these factors. These are some variations of attentions. The one that I discussed was a simple attention method, right? I basically discussed this one. This is called dot product attention, right? This is the one that I discussed. You can also think of some sort of parameter, right? Because we have a lot of data. We will be very happy if we are able to add more parameters, right? So you can also add a parameter between the query and the value, right? What you can do, you can pass the query to parameter matrix, right? You can also pass the value towards the same parameter matrix. It's basically a bilinear product, right? And then it will generate some vector. You can also think of doing some complex formula. For example, you concatenate the query and value, then pass it through a linear layer, right? Some non-linearity, then pass it through another linear layer, right? That will give you a vector, right? The transformer paper, they use something called scaled attention, scaled dot product, where we take the dot product and this dot product is normalized by the size of the vector. What is mod k? mod k is the size of the value, right, and you take the root of this. So this is scaled by the size of the vector. There is no intuition, by the way. I mean, these are different hacks, engineering hacks. Okay, so this is all about attention. We stop here, and in the next class we will discuss self attention and then the transformer model. Okay, thank you.